Thanks, Jules. Yeah, so I'd like to talk about Apache Spark MLlib, taking a look kind of at, its past, where we've come from, where we are now, and where the project seems to be headed. Just about me, I'm a software engineer at Databricks, working a lot on Apache Spark, especially ML and Graph, with a background in machine learning. Just quickly about Databricks, if you're not familiar with it, it was founded by the team which started the Spark project, now Apache Spark, at Berkeley in 2009, with a mission of making big data simple. And we're building and provide a unified analytics platform. So I will say, definitely try Apache Spark and Databricks. You can try it for free if you go to databricks.com. I won't be demoing it here. I'll spend the rest of this talk talking about primarily MLlib, but definitely recommend you check it out. Okay, so to start off, I want to take us back several years ago to when the first paper on resilient distributed data sets was published. And in this paper, one of the key results showing how important this Spark project was looking at ML on Spark, and basically showing that iterative algorithms like logistic regression and k-means can run a lot faster than in previous frameworks. So scalable ML has kind of always been part of the story. About 3.5 years ago, MLlib entered the Apache Spark project proper, and people added a lot of algorithms, classification, statistics, frequent item sets, linear algebra, regression, recommendation, feature extraction, clustering, and even more than are listed here. So it's really been built out to be a very versatile library. In fact, it is widely used in practice. There are a lot of production use cases, and these are just a few of the Databricks customers who have been using ML on Spark in production. There have been thousands of commits to the project, hundreds of contributors, and tens of thousands of users of MLlib on Databricks alone. So given this momentum, I want to take a step back and look at MLlib from the sort of what, so what, now what perspective. So the what is, how has MLlib developed, and what has it become? The so what is, given this trajectory, what are the implications currently for the dev and user communities? What have been the big impacts? And of course, now what is, where could or should we go in the future? So to look at the what, how has it developed and what has it sort of become at this point, I want to look at the past by doing a little data analysis. So I won't really have time to go through this, but basically I did some data analysis in a notebook, and I'm just going to look at the results, though. Cool. So this is looking at the algorithms added per Spark release from 0.8 to 2.1. On the left, or on the y-axis, is the number of algorithms added in each release. And you can see, the first release had a smattering of, classification, clustering, recommendation, regression. Some more classification algorithms were added. Then in 1.1, some featurization algorithms were added. And activity continued to grow, where in 1.5 and 1.4, a huge number of featurizers were added. But actually, the number of algorithms being added has sort of tailed off in more recent releases. But this isn't to say, if you look at the data, that the actual activity within MLlib has tailed off. If you look at the number of commits made to MLlib, not Spark, but MLlib itself, divided by the number of algorithms added in each release, you can see that a lot more work went into the last two releases of 2.0 and 2.1 per algorithm added. And the reason for this is essentially work has sort of changed from adding a bunch of new algorithms to building upon existing ones and adding infrastructure around them. This, I think, is a really great sign of the maturity of the project. Another cool thing to look at is the diversity of contributing organizations. We like stats, so measuring this using the entropy of the distribution over commits made from different organizations, where basically higher means it's more diverse. You can see in the initial release, there were really few organizations contributing to MLlib itself. But as the project has grown, the diversity of the development community has really increased, where there are a lot of organizations which are making significant contributions. So that is really exciting to see. Cool, so just to summarize, seen about 50 algorithms and featureizers in MLlib. There's been rapid development shifting from adding new algorithms to improving existing ones and adding infrastructure. And there's this growing, more diverse dev community. I think it's also informative to look at the major projects which we've seen. And keep in mind, these are my definitions of, quote, projects. They're not official ones, but they are based around major Jira and PR activity in different releases. So some of the ones I've found have been, first, trees and ensembles, of course, are a workhorse of industry, and a lot of work went into MLlib in the early releases to add these. Data frames came along, of course, and started to take over as the primary API for Spark rather than RDDs. And even though this started in 1.2, this work has really continued up until today in terms of porting RDD-based implementations and APIs over to data frames. This has had a huge impact in terms of nice integration with major projects like Spark SQL and structured streaming. Another big part of using data frames was the ability to tie this in to the idea of pipelines, stringing together ML workflows. And this largely occurred in 1.2 and 1.3. And I think one of the biggest impacts here was basically being able to handle algorithms with uniform APIs, especially for handling parameters for automated parameter tuning. Spark R came along. It had been a separate project, but was merged into Apache Spark in 1.4. MLlib APIs started being added in 1.5, and that's been filled out up until today. Of course, once you had pipelines, it was natural to add a lot more featureizers. And as you saw in the previous stats, a lot of featureizers were added in 1.4 and 1.5 in order to make pipelines really versatile and useful for pre-processing. And finally, of course, once you have these workflows, you want to be able to save and load them, deploy them in another Spark deployment, and so forth. And ML persistence was added to allow saving and loading both models and pipelines. The final project which I'll list is GLMs. And this came quite late, although there had been instances such as linear and logistic regression ever since the beginning. But GLMs, of course, are a workhorse of data science. And adding proper GLMs where you could get the model and result statistics was really important and was added in more recent releases. Cool, so this is a nice view of the major projects bringing us to today. And so now you can ask, so what? What are the implications? What have been the big impacts? I'd say one of the biggest ones has been integrating ML with the big data world. This sort of seamless integration with big data tools for SQL, data frames, graphs, streaming, and so forth has partly been within MLlib. And here I think some of the very cool things have been being able to use distributed data sources, whether that's CSV, Parquet, or whatever, just as easily as reading files off your laptop. Data frames have, of course, been very useful. They have, before they existed in Spark itself, of course, existed in tools like Pandas, R, and so forth. But adding these in a scalable way, tying with Apache Spark, has been huge for big data science. Having the ability to plug into graph processing systems in the same toolkit has been really valuable. I'd say maybe more even for developers, because some of the ML algorithms in MLlib are actually based on graphs, like EM for latent Dirichlet allocation and power iteration clustering. Streaming is also hugely important. As Tim and Michael demoed this morning, the ability to just take ML models fit using MLlib and deploy them into a streaming context has been very valuable. And with structured streaming, that's just become significantly easier. So this integration hasn't just been sort of what MLlib has done to integrate with big data. It's also had some impacts outside of MLlib. And here I'd phrase it as Spark and MLlib providing a sort of framework for integrating, quote, non-big data or specialized ML libraries. And when I say non-big data, I don't necessarily mean that these libraries can't handle large data sets, but they don't necessarily have the tooling to plug into, say, distributed data sources or the kinds of deployment modes you need in the big data ecosystem. Some cool examples include Spark sklearn, which is a pretty simple package for distributing some scikit-learn operations and basic ML tasks using Spark. The Stanford Core NLP integration package is another cool one, where it's essentially taking a quite complex ML package doing natural language processing, but providing it in a very simple API as UDFs for Spark SQL. Deep learning libraries were talked a lot about this morning by Matei and Tim. And this is one of the major focus areas at Databricks. As you heard in the keynote this morning, basically, this is a case where MLlib APIs, I believe, could have a huge impact on deep learning. A lot of deep learning libraries are, of course, quite difficult to get started with. And by using MLlib APIs, we hope that we will be able to sort of push forward the democratization of deep learning and also build on top of Spark for scalability. So some of the cool things here are like the deep learning pipelines library, which we talked about in keynotes this morning, BigDL in the Intel keynote, TensorFlow and Spark, if you heard Andy's talk earlier, and other projects as well, basically building APIs for tying together deep learning and Spark. And the final thing I'll mention, I think, in terms of a big impact, of course, is scalability. I'll divide this into two cases. One is workflow scalability, where essentially you can take the same code, run on small data on your laptop, and uncluster with big data. And of course, big data scalability in terms of scale-out implementations. And here, basically, all the MLlib algorithms are designed to scale out nicely. And there have been some impressive results. For example, this paper from last year showed that for deep trees applicable for random forests, it can be significantly faster than even libraries targeted at specific tree use cases. But this is also a case, I'll give the caveat, where there will always be room for improvement. In the same year, there was another paper showing that for shallow trees and gradient boosting, MLlib can still be significantly slower than XGBoost. So it's an area where we'll consistently be working. Oh, I should also mention, another final impact, which scikit-learn, of course, played a major role in, but which MLlib has sort of brought to the big data world, has been pipelines, building workflows from ETL, featurization, training, evaluation, and tuning. And this was done partly by introducing simple concepts, which most ML operations fit into: transformers, estimators, models, evaluators. And these sort of unified standardized APIs made it much simpler for users to understand how to use each algorithm. And secondly, pipelines for tying these together. And a big part of these were repeatable workflows across different Spark deployments and languages, tying in with data frame APIs, and also automated model tuning, which was made easier by this API standardization of how you handle algorithm parameters. So given these major impacts which this work has had, I want to ask, now what? Where could or should it go? And I'll give the caveat that, of course, this is my personal opinion, but I did try to collect a lot of feedback and information and queries from the Spark community. So some of the top items I've seen on discussions in the dev list include continued improvements to speed and scalability, enhancing core algorithms, providing ML building blocks like linear algebra and optimization, adding more extensible and customizable APIs. So I'll group these four really into three goals. I think two fit into one. The first being scale out ML, the second providing a standard library, and the third providing an extensible API, which includes providing building blocks to help with those extensions. So to talk about these quickly, scale out ML, of course, involves a lot of different changes, in part some of those changes do depend on specific algorithms. But I'd say that a big improvement which is coming is the move towards data frame-based implementations. Most of the implementations are still in RDDs. We'd like to port them to data frames to take advantage of things like Project Tungsten and Catalyst. This is still sort of in the prototype stage, but if you caught Xiangrui's talk earlier today, we can get major scaling improvements, even above 10x, for algorithms like connected components and graph frames. That said, there will still be the need for more targeted sort of algorithm-specific improvements. For example, one thing which makes XGBoost a lot faster with gradient-boosted trees is the ability to do feature subsampling. Also, linear models currently in Apache Spark generally max out around 10, or if you really push it, maybe another order of magnitude, million features. But if you try to push them up to billions of features, they will often fail. Now, there is work outside of Apache Spark, which Committer Yangbo Liang has given talks on, and vector-free LBFGS is a great option in this case, which would be great to add into Apache Spark itself to scale these models up to billions of features. So, to talk about offering a standard library of core algorithms, I'd say that the main algorithms are pretty much already there. I'm sure there will be more which will be added, consistently with every release. But in terms of the 80% use case, there are significant improvements to be made to some of those algorithms. For example, some currently handle bad values, not a number or null, smoothly, but not all do. Some handle instance weights, but again, not all do, and that should be changed. It'd be great to support more warm starts in order to sort of like provide initial models so that you can converge faster for some algorithms. And finally, multi-column feature transforms is another highly requested feature, basically for efficiency and ease of use. And there's some algorithm-specific improvements, such as for trees, it'd be nice to access, say, the tree structure from Python. But the one which I'd really like to focus on is talking about extensible and customizable APIs. So MLlib has about 50 algorithms. And the best way to look at sort of the need for extending and customizing APIs, I'd say, is comparing with the R repository, CRAN, which lists about 10,000 packages. So, basically, users must be able to either modify algorithms or write entirely new ones. And a nice way to sort of visualize this, I'd say, is if you look at sort of algorithm usage, MLlib sort of provides these heavy hitter algorithms, which most people want to start with. But there is this long tail of more esoteric or specific, application-specific algorithms, which are important, but which I believe really need to be filled out as third-party Spark packages. So if you haven't heard of Spark packages, it's available at this sparkpackages.org. Currently, it has about 340 packages for Spark, about 80 of which are for ML or graph use cases. There are some cool examples in there for ML. For example, one of my favorites is Graph Frames, which is basically data frame-based API for graphs. And that's actually seen a lot of adoption, including in major production use cases, like at the Capital One keynote last year. Bisecting k-means is a cool example because it was an algorithm added as a Spark package as a more scalable k-means algorithm. And now it's actually been adopted into Apache Spark itself. And then I'd mentioned the Stanford Cornell p-wrapper before, which is just a neat way or example of tying an existing ML library into MLlib. So in order to fill out this long tail of Spark packages, of course, people need to be able to write them. And so how do you write one? Well, at a high level, you simply need to extend an API like transformer, estimator, model, evaluator. MLlib provides some help. So if you have a very simple transformer, we provide an abstraction unary transformer. And in that case, it's really easy to write a custom transformer. We also provide some stuff for reading and writing algorithms or copying them. And if you do this, then you get, say, natural integration with data frames, pipelines, even automated model tuning. But there are some challenges. And so on the left, I'll list modifying existing algorithms with custom loss functions, optimizers, stopping criteria, callbacks. This exists in a very few cases in MLlib, but in general, the algorithms are not extensible in this way, unless you do some hacks. And being able to, say, plug in a custom loss function into a linear model would be a really valuable thing to a lot of data scientists. Implementing new algorithms is another case where there's some challenges. You have to write boilerplate. If you're writing it in Python, you have to worry about sort of API compatibility, especially around ML persistence. ML building blocks like optimization routines are not necessarily as easily available as they could be. And feature attributes or metadata, handling that, can be an important part of algorithms, but is a pretty esoteric and hidden API in MLlib right now. So just to give an example of these MLlib APIs, I want to return to the deep learning pipelines for Apache Spark package, which was mentioned in the keynote earlier. And here, I'm not really going to run a full demo. I'm just going to mention, like, this is a notebook using this library, deep learning pipelines, imported as a library in Databricks. And so we download this data set, and rather than looking at whether or not a photo contains a car which might contain James Bond, we're going to compare like daisies with tulips. Almost as serious. So this transfer learning workflow, which Tim had talked about in the keynote earlier, is a great example where after loading the data, importing some stuff, we can simply plug in this, in this case, a transformer from this third-party package, just like we would any other transformer in MLlib. You know, we could just as easily replace this deep image featurizer with, say, you know, hashing TF or some other transformer, which would take the input and convert it to a feature vector, which could then be consumed by other pipeline stages from MLlib or third-party packages. And of course, the really nice thing about this is you can plug this right into MLlib's automated tuning. Here we're building a param grid to estimate, you know, best parameters for our pipeline. You can plug that into, say, train validation split or cross-validation and fit it. And I won't actually run it here, but it's a nice example of like sort of the ideal thing users might want. So I'd say right now APIs are great for users. They offer sort of plug-and-play algorithms with a standard API. But challenges do remain. Development requires expertise, and the community in terms of the sheer number of packages, the usage, and sort of the habits of use and communication are still under development. So my challenge to you really is, can we fill out this long tail of ML use cases? You know, if you're a user, like, what is missing for your needs, and what's stopping you from finding or writing a package for it? If you're a Spark developer, do you see ways to make these algorithms more extensible or customizable, or do you have a cool package which you could publish but just haven't yet? And if you're a Spark committer, how can we better architect MLlib to facilitate this customization? So what I'd like in the end is for, like, you know, data scientist has an esoteric use case and needs a customization, and their default option is to say, I want to use the MLlib APIs because it's easy, and I know a lot of people will adopt it if I just push it to Spark packages. So I do want to leave you with some resources. So Spark packages is available, and there are also some cool tools. So the first one, SBD Spark package, is a plugin, which is helpful if you're building a package. There's also this tool for generating a package template. And there's a number of example packages which can be nice to look to as ways of, say, figuring out how to generate documentation or just architect the package. I also want to mention, like, unfortunately it's at the same time, but there's a cool talk from Holden and Seth, two other major contributors, on extensions to ML. So since you're missing that by being here, thank you, but you should definitely also check that recording out later on. So with that, yeah, thanks very much, and hopefully see you at office hours later today.
Thank you, Joseph. for the rather very instructive narrative framework within what, so what, and now what. So it's time for you to ask, so what? Any questions? There are 2 mics on either side of the aisle. Please do feel free and ask any questions. Nobody? Okay, well, give a big hand to, oh, go ahead.
So one question about data frame implementation.
Wait, I'm sorry?
Data frame-based implementation of ML algorithm.
Right.
So you listed up some example that can achieve the performance improvement. So how about the other algorithm for data frame implementation? For example, existing algorithm, if you re-implement using the data frame, can we achieve the faster performance improvement?
Yeah, it's a great question as far as like with data frame-based implementations, what can we expect? And of course, I mean, the easy answer is it will be algorithm dependent. But in general, I think like one of the most annoying things with MLlib is if you have been running it for, say, a number of iterations, and then, say, you start getting ooms or like out of disk space from, from needing to shuffle data, that kind of error. And essentially, like, data frames do address a number of these issues in a much smoother way than RDDs in terms of, excuse me, in terms of handling spilling to disk and other forms of like providing robustness much more smoothly. So I hope that that sort of extends to all implementations. But I do think that some in particular ones which do a lot of shuffling of data will benefit. So yeah, definitely looking forward to seeing that in the future. And essentially, like in terms of what's blocking it, the main thing blocking it right now are that data frames handle caching a bit differently than RDDs, so that in order to implement an iterative algorithm on top of data frames, like it's natural to want to cache between iterations, but you have to do a bit more manual work than with RDDs. So we're not quite ready to like port them all.
Go ahead.
Hi, great talk. If we think about compare the MLlib versus the many other larger scale machine learning libraries, from architecturally, I think there's one small difference. Currently, most all the ML algorithm is the driver, is a central point for the synchronizations. And the many new algorithms people have developed in the distributed ways leverage this parameter servers. And in the separate talk this morning, I think on the lab project in Berkeley, there was using the block managers as kind of as a way to implement parameter server. I just wonder, do you have any thought on expanding the architecture design patterns of MLlib to enable the community to extending the MLlib to do some parameter server type of things?
Right. Yeah, that's a great question about like sort of the fundamental communication patterns which MLlib is built upon. And there I'd say like, I mean, providing a parameter server framework would be very cool and would certainly allow some types of scaling which the current sort of driver-based reduction and broadcast pattern would not provide. I think maybe an initial step would be rather than, so I guess originally there was sort of like collect a driver, aggregate there. Next came the tree reduce or tree aggregation, so that could at least like parallelize some of that aggregation. Moving to providing sort of like an all reduce framework, which could, with some work like avoid having the driver as this bottleneck could be a really nice thing. But I mean, certainly for some algorithms, like parameter servers would be great. I know there's been work in outside projects for this, and it seems like the kind of thing which would certainly be useful to provide at some point in the future. I don't see that on the super near horizon, but it's also, you know, a community project, and like, yeah, I am looking forward to seeing what they do.
Thanks a lot. We're out of time. Joseph is going to be by the Databricks book for his office hours. If you have any more questions, do stop by. And give a big hand to Joseph, please.